good morning, everyone. We are working on right-angled triangles, which is kind of what I have here. It's essentially broken into two halves. It seemed to me that would be the natural way to do it. So in the first one, part A, we're going to be looking at naming the sides again of right-angled triangles, finding some missing sides and angles, but not so much of that. And the most part is going to be about creating a right-angled triangle and then using it to find the other 5 missing trig ratios. So a lot of this we covered on Friday, so hopefully this will go smoothly. And then we can maybe go into part B, where I think more of the interesting questions are. So basically a recap. That's what a right-angled triangle looks like. Right, it's got corner, it's got a right angle. There's an angle over here, the angle of interest. In this case, it's the bottom right-hand corner. And once you have this, you can then name the other sides. And one's called the opposite, one's called the adjacent, and the third one is called the hypotenuse, right? So just to start the ball rolling, this vertical line that my finger is going up and down on, what would the name of that one be?
Opposite.
Up. Yeah. And I think of it as opposite the angle. That's just how I remember it. So what's the second one, the other one that makes a right angle? The second straight line, I guess. There's one.
Adjacent.
Adjacent. And I can kind of remember that because the word adjacent, if you're adjacent to someone, means you're next to it. Do you see how that line's next to the angle? That's now the long sloping one, the one that's furthest away from the right angle, is called the hypotenuse. And essentially, there's a bunch of questions which gives you a triangle, and they ask you which one's called the opposite, which is called the adjacent, which is called the hypotenuse. Question 1 looks very like that. And then, connected to this, there's a mnemonic called SOHCAHTOA. And what that does is it allows us to remember what the sine, the cosine, and the tangent are in terms of the sides of a right-angled triangle. So the sine of theta, OH, is the opposite of the hypotenuse. Cosine of theta is the adjacent of the hypotenuse. And last but not least, the tangent of theta is the OA, opposite. That's first, A, adjacent is last. And that's 3 of the trig ratios. There are actually 6 trig ratios. And these are 3 of them. Now we're going to do the other 3. And they are going to be the cosecant of theta, the secant of theta, and the cotangent of theta. And to get a cosecant, it's essentially the reciprocal of the sine. So if you know one and you turn it upside down, that's what reciprocal looks like, you get the other one. So the cosine is adjacent over hypotenuse, so the secant is hypotenuse divided by the adjacent. The tangent is opposite over adjacent, so the cotangent is adjacent over the opposite. So for any right-angled triangle, these are the formulas for calculating the 6 trig ratios. Pretty much Friday, right? Nothing new here, seen it. So let's show you some questions involving finding the other trig ratios. So suppose I gave you a right-angled triangle. It goes theta. And I tell you that the sine of theta is 4/7. And I ask you to maybe draw the triangle and find the other 5 trig ratios, right? So you know that one, and our job is to find the other 5. So I got a picture, and if I don't have a picture, I will draw one just like this. And now I'm going to use this piece of information. I'm going to go and do the names again. So opposite, adjacent, hypotenuse. And then I'm going to use this piece of information. So I write it down here because I have more room. The sine of theta is 4/7. The sine is opposite over hypotenuse. So if you write next to it, opposite over hypotenuse, can you see that I can now see that the opposite is 4 and the hypotenuse is 7? So I can go here and say, you are 4 and you are 7. That makes sense? If you tell me the sine is 4/7, I now know what the opposite is, 4, and the hypotenuse, which is 7. So there's only one guy I need to now get, and that is the adjacent fella, right? And we use a Greek guy who figured out how to do that. There's your clue. How will I find the third missing side of this right angle triangle?
It'd be the square root of the hypotenuse squared minus the opposite side squared.
That is actually the whole thing in one go, which is totally correct. And do that, you're right. I was going to just start a little bit further back than that. Couldn't we do Pythagoras, which is the Greek guy? And the hypotenuse is 7, so there's the 7 squared you talked about. I don't really care which one I call A, right? I'll call that one A, so I guess the adjacent squared plus 4 squared, right? Because we only need to have one missing, so I've decided A for adjacent. And so the adjacent squared is 49 take away 16. So the adjacent is the square root of that, which I believe is 33. And now we have all 3. And then you can find all of these guys, because don't they all have their own little formula? I'm not going to do the other 5, that's just waste of time. But for instance, if I wanted to know the cosine of theta, it would be the adjacent over the hypotenuse. And that would be, in this case, the square root of 33 over 7. If I wanted to get, say, the cotangent of theta, then I would have adjacent divided by opposite. And that would be what, square root of 33 over 4, and so on and so forth. So once you've got this triangle built, can't you find all of these guys? I've only gave me a couple of them, but you can find any of them just by, picking the right formula and adjacent over hypotenuse. Things that you might have to do, hadn't harmed in any of these questions, but can you imagine I did a question and the answer was 7 over the square root of 33? Sometimes that might happen. If it did, you could make it look pretty, and you could rationalize the denominator. I think WebAssign is pretty generous about not bothering if you forget to, but it is a good idea to do it, right? Makes it look pretty. Style points. Any questions so far? Pretty straightforward. Build a triangle, get your formula. See if I can pick one then. This is question 4 from the homework. And they ask you, to find the sine of theta. And they want the answer to be in terms of A and or B or C. So this question doesn't have any numbers, but it's still similar to this one. What is the formula for calculating a sine?
Opposite over hypotenuse.
Okay. Now, most of the time, won't these be numbers? But in this case, opposite and hypotenuse are all going to be letters. And I'm running short of space here, but this is the opposite, isn't it? And this here is the hypotenuse. And this here would be the adjacent. So if you want opposite over hypotenuse, you would just say B over C, right? And that's the answer. Right. If these had been numbers, wouldn't you do it more like this? Try to find another one with numbers before I move on. Ah, perfect. Found one. Question 9 says the tan of theta is equal to the square root of 3. And it asks you to find the other 5 trig ratios, right? Pretty standard question. Now, I'm going to build my little right angle triangle. I'm going to call that theta. I'm going to have opposite. I'm going to have adjacent. And I'm going to have hypotenuse. And I hit my first problem. The tangent is opposite, right, over adjacent. Agreed? And normally, shouldn't there be a fraction here? So the top guy is opposite and the bottom guy is adjacent. Right? But there is no fraction here. How do we get around that issue?
Couldn't it be over 1?
Yeah. Just do that. So now I know that the opposite is the square root of 3 and the adjacent is 1. You see how that works? So if there is no fraction, make it a fraction by putting the number over 1. And now you've got a guy in the top and a guy in the bottom. You know who they are. And to get the hypotenuse, can you trust me? It ends up being the square root of 4, which is 2. So I'll just do it in my head. Now, once you've got that guy, can't you get all of them, right? The other 5. So just because I want to, I'm picking one at random. If I wanted to get the secant, I would do hypotenuse divided by the adjacent. And that would be 2 divided by 1. And that would be the nice answer too. And can you get the other 4 as well? I think things are going pretty good. I don't see too many scared faces. That's a good sign. Do I need to do another one of these? No. Done one like that. Yeah, done one like that. Right, I'm not doing all of 13. I'm just going to set it up. So, right angle triangle. Make this angle in here theta. Opposite, adjacent, hypotenuse. And in question 13, you are told that the cotangent of theta is 3/2, and you're being asked to find the other 5, as I'd expect. So the cotangent is the adjacent divided by the opposite, right? So in this case, the adjacent is the top one, 3, and the opposite is this one here, so that's 2, and 9, 4. And if you do Pythagoras, you can just trust me, you've got 13. Once this triangle is created, would you agree getting the other 5 ratios is pretty much plug and chug? Right? Pick whatever the formula is, plug in the numbers, Right, pick whatever the formula is, plug in the numbers, and you get all of them. So I'm going to leave that. I think we've covered enough of that. So if I gave you just randomly, you know, something like this, right, a piece of information, one of the 6 trig, right, it could be any one of these 6. If I gave you one of these and I told you what it was equal to, could you build a triangle that would represent this information and then get the other 5? Do you feel comfortable you could do that? Right, I see nods, so I'm going to say, yep, you feel comfortable about doing that. So we don't need to do any more of them. So the next thing on my little list, where is my little list? I threw it away. Here we go. Oh. That one. So finding missing sides and missing angles. That's the next topic. Okay, so imagine that I give you a right angle triangle and I tell you that this angle here is 33 degrees. And I tell you that this side is 5, right? That's all you get. No more information except that. And we want to find all the missing angles and all the missing sides on this triangle, right? All the missing angles and all the missing sides. So from this angle's perspective, that's going to be called the opposite. This side here is going to be called the adjacent. And this side up here is going to be called hypotenuse. Have you noticed that Pythagoras is no good? I can't use Pythagoras to find anybody, right? So I'm going to have to find the missing sides some other way. I'll show you how you do that. But before we worry about that, let's get that missing angle.
I remember how to do that. And
Go
that
for it.
missing angle is 57 degrees.
Do
Because
you
it
want
just
to
took
tell?
180 minus 90 because we have a 90 degree minus 33. And then the resulting number is that last angle.
That makes sense, guys? That is always 90 because it's a right angle triangle. This one happens to be 33. What's left? 57. Right? What's left from 180? So check that off our box. Would you agree finding, at least in this question, wasn't finding the missing angle pretty straightforward? I didn't need to do anything too clever. Now things get a little bit less clear. I need to find one of these 2 sides first. And it really doesn't matter which one I decide to get, because you're going to get the right answer. If I want to find the adjacent first, or if I want to find the hypotenuse. So here is a question. Will someone tell me which one they want me to find? Because it doesn't matter. Pick a one.
Let's go hypotenuse first.
Okay. So put a little bubble around it. And put a little bubble around any side that you know the name of. So do you see I've got opposite, I've got a bubble around it because I know it's 5. And hypotenuse, I've put a bubble around it because that's the one I want to find. So what you now do is you scan through, and don't even worry about these bottom ones. They're not helpful. Use the top 3. Scan through the top 3 and find out which one uses an opposite and a hypotenuse, because that's the guy we're going to be using. So which one of them, the sine, the cosine, or a tangent? Which one uses opposite? Say again?
Cosine.
Cosine. So are you sure? Which one uses opposite and hypotenuse?
The sine.
Yes. Oh, I thought you said something else the first time. Right. So the sine of theta is going to be the opposite over the hypotenuse. Do you see how I decided on that one rather than the other 2? Because that's the only one that uses these 2. Then you replace theta with 33 degrees, and you replace the opposite with 5, and now you have got that guy, right? And all we need to do now is figure out some mathematical way to find the value of the hypotenuse. I suggest strongly that you do that. Can someone tell me what is going to happen next, especially because of what I did here?
You cross multiply.
Yeah, you see me doing it? Cross multiply. So it's going to be the sine of 33 degrees times the hypotenuse. It's going to be 1 times 5, which is 5. So what do you do to both sides to find the hypotenuse?
You divide by sine 33.
You all agree you divide both sides by the sine of 33 degrees. And I am now about to do a deliberate mistake. And it is a deliberate mistake if I tell you before I do it, right? So this isn't just one of my normal mistakes. This one I'm actually going to actually do in purpose. Right, so
Question
5.
beforehand.
Oh, I think you figured out what I did, even before I did it. Now, the answer I got could be correct. It could be that the other side is 5, right? The hypotenuse is 5. It's unlikely, because the degree of the hypotenuse should be a little bit bigger because it's the longest. And what was it someone said I did wrong?
Don't we need to be in degrees instead of radians?
Correct. And
Yeah,
have
that's
you?
what I was going to say.
Yeah, that's exactly what it is. So now you go 5 divided by the sine of 33. And you see it's a quite different answer. And let's assume that they want the answer to just 1 decimal place. So 9.2 would be the rounded off answer. I don't know how many times in my life I've done that, where I was in radians when I should have been in degrees, and where I was degrees when I should be in radians. For the last week or so, haven't you just kept it in radians because that's what you needed to do, right? And have you noticed that now they're changing the rules on us? Right. Now, that gets us to a nice place. I now know that guy. There's only one guy left to find, the adjacent. How do you think I could do that? Any suggestions?
The
Pythagoras theorem.
Pythagoras
Yeah.
theorem works. So, well, you knew what it was, you just couldn't remember what the damn thing was called, right? 9.2 squared plus the adjacent squared. Let's try that again. 5 squared plus the adjacent squared equals 9.2 squared. So 25 plus the adjacent squared is whatever 9.2 is when you square it. And I get
84.64.
Yeah, that's what I get. And so the adjacent is going to be that guy, take away 25. So the adjacent squared is 59.64. So the adjacent will be the square root of 59.64. So square root of the answer. And I get to 1 decimal place 7.7. And you can use Pythagoras to find that. What other method, totally different from what we just did, could I also use to find the adjacent? And I'm saying 7.7 or 7.2, that is 7. There we go. What other way could I use? So,
Couldn't you do the tangent of 33 is equal to 5 over your adjacent?
I could. And I could have done the cosine of 33 is the adjacent over the hypotenuse as well. So the last guy has got lots of ways to find it. If you like Pythagoras and it's easy to do, you just use Pythagoras. It's going to work fine. Just saying there's options, right? You could do it other ways. Any questions about that, or you feel comfortable about the from start to finish what the process looked like?
So for Pythagoras theorem, you can only use that when it's a 90-degree angle, right?
Correct. Don't use it if any other triangle.
All right, thank you.
Right now, that's the only ones we're dealing with, but in the future, you're going to get other triangles. So it's a good point not to do it when it's not a right angle. No. Checking time here. Okay, this is a version of question 10. Try to do it the way they've written it. They call that X, but in the question, they then tell you X is 91. So I'm putting 91 there. We are being asked to find basically all the bits that are missing. So from this angle's perspective, what's the 91 going to be called? Opposite, adjacent, or hypotenuse? What's this side here? What's its name? Okay. This guy here. Adjacent, this one up here. Hypotenuse. I'm going to put a bubble around that guy. And just like we did the last time, can't we get to pick? Which one do you want to get next? Adjacent or hypotenuse? I think you said adjacent, is that right, Cassandra? Okay, so we're going to get that one. Oh, and by the way, I almost forgot. Isn't this guy in here, too tiny to do, isn't he 15 degrees? You happy about 75 and that one in 90? Right, so back to our quest. I have opposite and I have adjacent. So I need to find which one of the trig ratios uses opposite and adjacent. Oh, and I won't show you this time. See if you can do it from memory. Opposite and adjacent. Which one uses those two?
Tangent.
You nailed it. So the tangent of the angle is opposite over adjacent. So the tangent of 75 degrees is 91 over adjacent. Little cross multiply here. Tangent is 75 degrees times the adjacent is 91. So the adjacent, now you get that by dividing both sides by the tangent of 75. So I go here, and I go 91 divided by tangent of 75, and the answer to 1 decimal place at least is that. So I can now put in 24.4. Now I'm not going to finish this question off, but couldn't we find the third missing side, the hypotenuse, by using Pythagoras or one of the other trig ratios if you want to do it that way?
I have a question.
Yes. Yeah, what's your question? If you're talking, I cannot hear you.
So when I found, instead I found the hypotenuse,
Okay.
and then when I went to go find the adjacent side, I got 24.3.
Right. Interesting problem. And you might think, well, they're not the same, which they're not. Do you know that's been caused by rounding off errors? That's all. So if you did I'm doing it to 1 decimal place because I'm lazy, but let's suppose you had to do it to 2 or 3 or 5 decimal places. Make sure that you always round off to as many decimal places as you can, and then only at the end do a rounding off. So that's all that's happened here, just some rounding off errors. So if you do that and WebAssign says no, just add or take away 1, right? So if 24.3 doesn't work, try a 24.4, try a 24.5, and that will work. It isn't that you've done anything wrong, isn't it? Just rounding off. Sometimes, you know, if you're unlucky, at least they all work in the wrong direction and make your answer a little bit out because of that.
So then what if I do on one of the tests, I have 24.3 instead of 24.4? Would that be?
Oh, that's not a problem, because the only test that well, let's rewind that. If we're talking online tests, I always look through them, so I will fix that. So
if
you'll
I'm
get the
off by
points.
like 0.1, it's not going to harm me.
Yeah, I will know if you told me the answer was 24.4 and WebAssign says it's wrong, and I'll know that the answer is 24.3, and I can tell that's a rounding off error. Now, if you say it's 29.7, then you're wrong, okay? But if you're 24 point pretty much the same number, then I'm just going to assume it's a rounding off issue and you get your points. If it's during the midterm, where you write down your working and I get to see it, it's even easier, because in the midterm, if you do a different mistake somewhere early on, in which case your answer might be quite different, I can still follow the process because you'll write it down, hopefully something like this, and you still get partial credit. So in the midterm, it's a lot easier for me to see what you've done wrong. In WebAssign, I can only fix those kind of mistakes like these, because I can tell what you've done.
Okay.
Okay, are we good with these questions? So if I give you a triangle and I give you one side and one angle, like I did these, do you feel comfortable about the process to find everybody else? Right. The missing angle's a baby, right? You can always get that easily. And then the 2 sides after that. Scanning through. Covered that. Covered that. Be anything I've missed? No. Okay. So unless there's more questions, we're going to move on to part B now. Are there any questions? Tony? Anthony?
No, I'm good now.
You good? Okay. Go away. No. My dog's decided to come in and bug me. She's still a baby. She needs lots of attention. Fortunately, I can't always give her it. Right, so that's what we're going to deal with. So what is left in the right angle triangle world that we have still to do? I'll answer is a lot. There's a lot of things we haven't really covered. I would basically describe all of these as problem questions now. What do I mean by that? You are going to be given shapes with right angle triangles in them, and the problem's going to be to find a missing side here or a missing angle there. But it isn't always going to be as straightforward as, you know, oh, I only need to do this one step and I'll get the answer. Sometimes you have to find a missing side first before you can find the angle that you're looking for, right? So it can be a 2, or even in some questions, a 3-stage process. You can't get the guy you've been asked until you find 2 other guys first, right? That kind of ABC kind of situation. So let's start forward with much simpler ones, and that's this one, this situation here. A nice right angle triangle. We're going to find the missing angle. Okay, so this is a nice simple problem, nothing too scary. From this angle's perspective, this side is going to be called opposite. This one is going to be called hypotenuse, so it's very similar to what we've been doing. Not a lot of changes yet. Trying to find my piece of paper. So it'll be the last one, won't it? How can I lose a piece of paper on a desk? How can I do that? I've got a knack. My dad had a saying, I could lose myself in an empty house. Which is kind of hard to do. There we go. Technically, that side there is adjacent, but I'm not interested in him. You put bubbles around sides that you know the length of, or sides that you're trying to find, right? So in this case, I know two sides, so I'm going to put a little bubble around each of those. Which one of these top three, right? We don't care about the bottom. Which one of these uses the opposite and hypotenuse?
Sine.
Okay, so you would say the sine of x degrees is opposite over hypotenuse. So you would say the sine of x degrees is 5/7. So now we can find the missing angle. And we're going to let the calculator do it. Remember we did those inverse sine, inverse cosine stuff where you had to find inverse sine in 3/2 and all that? I'm going to do something a little bit different, but still using inverse sine. I'm going to take the inverse sine of both sides. And the inverse sine of a sine gets you x. Does that make sense, what I just did there? The sine of x is 5/7, so x degrees is the inverse sine of 5/7. Technically, what I'm doing is taking the inverse sine of both sides. The inverse side of that side is this thing, and the inverse sine of a sine, they cancel out and you just get the x. Analogy. Do you know if you want to get rid of a square root, don't you take the square of both sides? If you want to get rid of a square, don't you take the square root of both sides? If you want to get rid of 2x, don't you divide both sides by 2? Isn't there something you can do to both sides that gets rid of the guy? I wanted rid of this sine x, so I did it by taking the inverse sine. And now we can hit buttons on our calculator. Inverse sine, oops, put it on. Inverse sine of 5/7 is 45.6 degrees to 1 decimal place. Are we comfortable with that? How to find a missing angle? Right. If you know two sides of a right angle triangle, can't you find any missing angle? In this case, this one.
I have a question really quick.
Yes.
So you know how when we asked you in office hours one day when like the order of sine and inverse sine matters, like just like with tangent. So does it matter here in this instance?
Thank goodness, no.
Okay.
It's always going to cancel out.
Okay.
Those inverse sine, cosine things, you know those weird ones where the inverse tan of the tan of something wasn't always the thing inside it because of the standard angle issue. And in these questions, the angles are always going to be in a right angle triangle, these ones. And so that the guy that you get works perfectly. In other words, inverse sine takes care of it. You don't need to worry about weird stuff.
Okay.
Makes life so much easier.
Yeah,
And
thank you.
the reason that works is that these angles are always going to be less than 90, right? Because they're in a triangle. And if they're in the first quadrant, that rule about them cancelling out is true, right? It works all the time. So here is our first real puzzle, right? Something that's got a lot going on. So, right angle triangle looks like this. And we've got another line coming down here. And we are being asked to find that guy. And we know this there is 30 degrees. We know this guy here is 60 degrees. Obviously, this is a right angle. And we also know this side, which they call A, but then they tell me it's 94. So I have got a picture which contains right angle triangles. And in this picture, there is one angle or one side that we're being asked to find. In this case, they want me to find that side. Now, the way that you approach these questions varies a lot. It kind of depends on what does the picture look like. It kind of depends on what things they tell you in the picture, right? What this is equal to this and so on. So that makes this a little bit more of a one-off question. So this is how my brain works. First thing I tend to do is I try to find any side and or angle that I can get. So if you ignore that piece and only focus on this right angle triangle, would you agree that that angle up there is 30 degrees? Does that make sense? Right. Now, I know what that angle there is.
Can you do special right triangles?
Say again,
Can you do special right triangles?
what's that? I'm not sure
Like-
that firm.
Well, you know, like the rules with like 30, 60, 90 and 45, 45, 90.
Oh yeah, yeah. That's an example of a special triangle. I'm lazy. I just say, look, 90, 60, what's left, right? Because the next time that could be 42 degrees, right? And you have to figure it out.
No, yeah, but like to solve it, like to find out like the adjacent. I forgot how it works, but like, isn't it like the hypotenuse is like root 2? Or
Oh, I know the guy you're talking about. No, don't do that.
okay.
It would work on this question, but I want you to be able to do it for all triangles, not just for a special one, right? You know, like if you got a triangle that was 45 degrees, there's shortcuts for that as well. But I don't want to do that special triangle either. So these numbers are nice, but pretend they were horrible. This method's still going to work, right? Now, back to you. What's this guy called? How big is he?
120 degrees.
You want to tell, correct? Do you want to tell people how you figured that out?
You know, the line on the bottom is 180. 180 minus 60 is 20.
Agreed. Lines are 180. So if you know one side 60 isn't the rest, what's left? And while I'm at it then, why don't I find this guy?
$30 degrees.
And do you want to, correct? Do you want to tell people why?
180 minus 120 minus 30 is 30.
So triangles add up to 180. You know two of them, what's left is your answer. Right, so a lot of those green angles may or may not be useful, but you don't know if you're going to need them until you put them in, right? So that would be my first step in this question. If there's any sides or any angles I can write down without doing too much work, do so. Now I have to figure out where to go next. And I can think of, oh God, I can think of about 3 different approaches, all of which work. So that's nice. Anybody got any idea what side I find next. I'm not going to be able to get X yet, but what other side can I find?
Could you figure out what the very bottom line of the whole line?
I hear your voice, but I couldn't really pick up what you said.
Could you figure out, if you look at the 30 degrees, could you figure out what the adjacent side is by doing the tangent of 30?
Right, this 30 degrees here or this one?
The one on the orange. The orange 30.
Oh, this one here? Right, and you wanted to find which side?
The adjacent side.
So you're talking about this big side here?
Yeah.
Oh, that's an interesting way. Yeah, that's one of my three. So what you got to imagine here, if I can just draw a baby version of what you said, is see this line here? Pretend it isn't there. Pretend you've got one huge big triangle. Then don't you know this is 94? Don't you know that this is 30, right? And if you put these together, isn't this guy up here 60? And if I'm interpreting you correctly, you're saying, why don't we find this side here called the adjacent? Is that your thought process?
Yeah.
Yeah, that's mine. Now, you can definitely find that. And yeah, let's just do it that way. As I said, there's three ways to do it. Might as well do it that way. So in this story, this side over here is going to be called what? The opposite, right? So I have an opposite and adjacent, right? So I'm going to do the tangent of 30 degrees is the opposite over the adjacent. And so the tan of 30 degrees is going to be 94 over the adjacent. Do the little cross multiply thing. The tan of 30 degrees times the adjacent will be 94. And so the adjacent will be 94 over the tangent of 30 degrees. And let's do that in the calculator. 94 divided by tangent, I know you're here somewhere, 30 degrees. And the answer I get is 162.8. Okay, so I now know that this guy here is 162.8. That's good. I need to find another side now. And once I find this second side, then I'll get X. So who do you think I need to find the side of now?
Hey, you not do the same thing but for the degree of 60 degrees and then subtract that from the full?
That's exactly what I'm going to do. So what we're going to do now is we're going to find this little guy, which means forget about that triangle and focus on this little one. And I don't really have a lot of room for him, but there's a 94 here, right? There's a 60 degrees here, and I want this fella, and I'm going to use that one to name the sides. So that's going to be opposite, that's going to be adjacent, and that's the guy I'm going to find, right? This guy here. And since I don't have a lot of time, imagine me doing all of this work, and the answer is going to be 94 divided by the tangent of 60. And I get 54.2. Okay. And
Wouldn't that be
X,
54.3?
yep, it will be. And X then is going to be the whole thing, 162.8, take away 54.3. And 162.8 take away 54.3, and the answer we got is 108.5. Okay. I think that definitely qualifies as a problem question, doesn't it? Now, I said there's at least 3 different ways of doing that. You might come up with a totally unique way. Katie, for instance, was wanting to do standard triangles once she's figured out how to use them. That method would work in this case because these numbers are angles, are standard triangle angles. I'll let you figure out other ways. The cool thing is, it doesn't matter which way you work or you do it. It just needs to work, doesn't it? If it gets you the right answer. Now, some of you will do the scenic route, which means that you might well find all sorts of angles and lines that you don't need to find, but eventually get to the answer. And some of you take the shortcut, where you find a very efficient way of doing it. And that doesn't matter. It's better if you could do the shortcut route, but at least you got the answer. And the bottom line, that's important, isn't it, that you got the answer? So last name and bye-bye, time up.